Dijkstra's shortest path algorithm is one of the foundational algorithms in computer science and graph theory, designed to compute the shortest path from a single source vertex to all other vertices in a weighted, directed or undirected graph, provided that all edge weights are non-negative. The algorithm, developed by Dutch computer scientist Edgar W. Dijkstra in 1956, is a classic example of a greedy strategy that builds the optimal solution step by step through locally optimal decisions that are guaranteed to lead to globally optimal shortest paths. At its core, Dijkstra's algorithm maintains a set of vertices whose shortest distance from the source is already known and a priority queue of candidate vertices based on their tentative distances, which initially are set to infinity except for the source, which is set to 0. The algorithm proceeds by repeatedly selecting the vertex with the smallest tentative distance. This vertex is considered settled because once chosen, its shortest path distance is final, and then relaxing all edges leaving that vertex. Relaxation is the crucial operation that checks whether reaching an adjacent vertex through the newly settled vertex offers a shorter route than previously recorded. If so, the tentative distance of that neighbor is updated, and the priority queue is adjusted accordingly. This process continues until all vertices are settled or until the target vertex is reached if one is specified, making Dijkstra's algorithm both a single-source all-destinations algorithm and a single-source, single-destination algorithm. Depending on usage, the correctness of Dijkstra's algorithm rests on the fact that once a vertex is extracted from the priority queue, no shorter path to it can ever be found due to the non-negativity of edge weights. Thus, the tentative distance at extraction time is indeed the shortest possible. The efficiency of Dijkstra's algorithm depends significantly on the underlying data structures used to store and retrieve vertices with minimum tentative distance. In its most naive implementation using an array or linear search, the algorithm runs in V2, which is acceptable for dense graphs where the number of edges is close to V2. However, when using more advanced structures such as binary heaps, priority queues, the complexity improves to V plus E log V. And with Fibonacci heaps, it achieves an even more efficient E plus log V. Although Fibonacci heaps are more theoretical and rarely used in practice due to implementation complexity, they demonstrate the algorithm's capacity for optimization. Modern software libraries, such as those used in GIS systems, routing software, and network simulations, typically rely on binary heaps for a balance of performance and simplicity. Because the algorithm processes edges only when necessary and uses prioritization to minimize exploration of irrelevant vertices, it is exceptionally efficient for large sparse graphs, which represent many real-world systems like road networks, communication infrastructures, and social graphs. One of the most important features of Dijkstra's algorithm is its versatility in representing different real-world shortest path problems. In navigation systems, such as GPS route planners, Dijkstra's algorithm serves as the foundation for finding the fastest or shortest route across a city or a country. Roads are modeled as edges with weights corresponding to distance, travel time, or traffic conditions, and intersections or locations represent vertices. Systems like these often apply optimized variations such as bidirectional Dijkstra, a search, and contraction hierarchies to improve performance while preserving correctness. In computer networks, Dijkstra's algorithm forms the basis of routing protocols such as OSPF, Open Shortest Path First, which uses link state information to determine the most efficient path for data packets across a network. Here, the graph represents routers, and edge weights reflect transmission costs. delays, or congestion levels. In robotics and AI path planning, Dijkstra's algorithm helps robots determine safe and optimal paths through grid-like environments, especially when paired with cost maps where each cell has a movement penalty. Beyond direct practical use, Dijkstra's algorithm has profound theoretical significance. It illustrates the power of the greedy algorithmic paradigm, demonstrating how local choices, selecting the nearest unsettled vertex, can lead to globally optimal results when certain conditions, such as non-negative weights, are met. This aspect makes Dijkstra's algorithm a cornerstone example in algorithms courses, where students learn about graph representations, data structures like priority queues, and algorithmic proof techniques, particularly invariant proofs. The algorithm also introduces the concept of relaxation, a mechanism fundamental to many other shortest path algorithms such as Bellman-Ford and even more advanced techniques like Johnson's algorithm for all pairs shortest paths. In addition, the algorithm naturally leads to discussions about algorithmic limitations. Dijkstra's algorithm cannot handle negative weight edges, because the greedy choice becomes invalid in such cases. A vertex extracted with minimal distance might later receive a shorter path through a sequence of negative edges, violating correctness. For negative weight graphs, Bellman-Ford or SPFA, shortest path faster algorithm, must be used instead. Another important aspect of Dijkstra's algorithm is its adaptability. Numerous variants extend its power. Bidirectional Dijkstra searches simultaneously from the source and the target, meeting in the middle and significantly reducing processing time in large graphs. A star search enhances Dijkstra by incorporating heuristics, such as Euclidean or Manhattan distance, allowing it to prioritize paths more intelligently and dramatically speed up route finding in spatial graphs. Multi-source Dijkstra allows computing shortest distances from several starting points, useful in service coverage problems, such as finding the nearest hospital or distribution center. When optimized with techniques like lazy deletion, decrease key operations, and geometric structures like quadtree partitions, Dijkstra's algorithm scales to millions of nodes, supporting massive real-time systems like transportation logistics, emergency response planning, and large multiplayer game maps. In addition to problem solving, Dijkstra's algorithm contributes significantly to visualization and understanding of graph structures. Each execution of the algorithm essentially grows a shortest path tree from the source, revealing how distances propagate through different areas of a graph. The shortest path tree allows insight into the graph's geometry, bottlenecks, and connectivity, and it supports further algorithmic steps, such as reconstructing paths by following parent pointers. This reconstruction capability is vital in applications like generating turn-by-turn navigation instructions, reconstructing packet routes, or analyzing cause-effect chains in dependency graphs. Ultimately, the enduring relevance of Dijkstra's shortest path algorithm stems from its unique blend of simplicity, efficiency, correctness, and practical applicability. More than 6 decades after its invention, it continues to be a core component in modern computing systems and algorithmic theory. Whether guiding a vehicle through a busy urban grid, routing packets across the internet, directing a robot through a maze, or enabling complex graph analysis in scientific computing, Dijkstra's algorithm remains one of the most important tools in the algorithmic toolbox. A testament to the power of elegant and well-founded computational ideas.